are we all doing? Monday. We have just a few announcements. So we have an alignment assignment, not a tongue twister, due on Wednesday. I'll be getting a new assignment to you by about then, but we have quite a bit to cover before that assignment can be reasonably assigned. We're starting a unit on graphs, graph algorithms, graph analysis. So we'll be starting that. The next exam will be a week from this Friday. I know it's still farther away than the last one was, but just getting it on your radar. I will have a study guide to you by Friday so that you can start studying for it. I think that's just about it. There's not too much else going on at the moment. I'll have office hours after class, helping you with anything with regards to the assignment or anything else. Any questions before we dive into graphs?
Will next week's exam cover graphs, or up to when are we covering?
That's a good question. I'll have to figure that out by the time the study guide gets posted, because there will be, depending on when that assignment is due, how much of that assignment is going to be relevant to the outcomes to the assignment or to the exam. I think that it will probably be relatively similar to what we did with ABL, where what we do in class is a little bit different from what we do for the assignment. So I can probably throw a lot of what we cover in class because the implementation details wouldn't be covered as much on the exam, but we'll have gone over a lot of that in class. So probably the answer is yes, at least in some capacity. To whatever extent it is complete, I'll have to make that decision.
So far, we pretty much just programming.
We have dynamic programming and greedy algorithms, and that's about it so far.
Yeah,
So we definitely need to cover some graphs things in order to make an exam remotely interesting and not just those two topics. All right, into graphs we go. So who has some experience with computer science graphs? This is not math graphs, this is vertices and edges.
I have some experience like statistics and stuff.
This is vertices, edges, edge weights. So you imagine vertices being circles and edges being lines connecting those circles with particular weights on them.
It's familiar, but
it's familiar to some, few.
But
yeah, those
two again, but still.
I think the three people in here who took my algorithms class, no, my data structures class, 3 or 4 people who took that definitely saw this in there. This is in fact a reuse again of some of that material, as I will expand on that and go into some new material. But we'll at least start by introducing the concept from what would be reviewed for the 3 or 4 people in here for which that is review. But it kind of belongs in a data structures class. That's why I go over it in data structures, because it is a data structure. So it seems strange in an algorithms class to be going over a data structure, but it is a data structure that has a ton of algorithmic support. There's an entire field of study that is graph theory. So rather than just introduce it a lot of the time here, at least, we push that off into algorithms so that we can introduce the last structure and then talk about all of the algorithms that we can run on graphs.
Now I understand.
So of everything that you've seen so far in data structures in here, it's really the last major structure, but it's probably the single most important to know at a deep level, because a lot of what we do on a day-to-day basis in this field operates on graphs. You go into networks are visualized as graphs. You go into any kind of data analysis, being able to look at that data as a graph is very important. So in general, they can represent any relationship among items. This makes sense, but graphs can come in a few different forms, which we will talk about. And there are a lot of terms that you need to know going into talking about graphs. So let's talk about exactly what they are. Defined to be a tuple, a set of vertices and a set of edges. So 2 elements, but each of those elements are sets. A vertex is just a node. It's very much like a tree node. It has a value, and then it has connections to nodes that are around it. A tree has a parent, a left child, and a right child. That's a binary tree. Otherwise, it might have an arbitrary number of children, but there's a hierarchy to it. There is no necessary hierarchy to a graph, but a given node does have a key, and then it has connections to some number of nodes around it, 0 or more nodes around it. So B, when we define that graph, is just that set of n vertices. Here, B sub 1 would be a vertex, up to B sub n would be a vertex. There would be n vertices in our graph, and B would be that set of vertices. An edge is that connection, very much like a reference in a tree, a directed connection between a node and its child or a node and its parent. It doesn't have to be directed or undirected. The idea is just that there is a connection between these two nodes. What that connection is, if it has a weight, if it has a direction, that depends on the context of the graph. So we could have an undirected graph. This means that when two vertices are connected by an edge, that edge does not have a direction to it. So we have two people who are friends on Facebook. There's no direction to that necessarily. It is a bi-directional relationship. These two people are friends. A directed graph, also called a digraph for short, because who likes syllables? There is a source and a destination to every edge, so they are directed. Coming out of one vertex, there is an edge that goes into another vertex. So just because there is a connection between vertex A and vertex B directed out of A and into B does not mean there is a reverse edge out of B into A. A into B, out of B into A, doesn't matter. Of course, not every vertex must be connected to every other vertex. Again, that depends on the graph. So some vertices will be connected to some other vertices. Some other vertices may not be connected to any vertices. They might just be alone in the graph with no connections whatsoever. Ahem, my social. Yeah, sorry. Any questions? Yeah.
So the data in the edge in the vertex.
Depends on how the graph is set up. So usually a graph is set up as some collection of nodes, and each of those nodes are their own objects. Those nodes can have something like an array of edges or a list of edges of some capacity, because it doesn't matter what the structure is, but yeah, it'll know what vertices it's connected to, but whether that's embedded in the graph itself, it's probably in the vertices. But there are some implementations of a graph where you can always query edges from an outside perspective. Depends on the implementation. We'll actually talk about that in a little bit. That's a good question. Other questions before we move on? All right. So let's give some examples. What are the vertices and what are the edges in the following examples? We have the web pages with some links. So yeah, they would definitely be directed for sure. What are the vertices in this case?
Pages.
The actual pages themselves? Yeah, that's the structure. So the vertices are the structure to the graph. The edges are the connections. So the links represent connections between web pages. And they're directed because just because there's a link from page A to page B does not mean there's a link from page B back to page A. We're not counting the back button as a link. How about Facebook friends? What are the vertices? What are the edges?
Well,
Yeah, so we have kind of a profile
yes,
as a vertex.
Yeah, that's pretty much it, and the edges are, the. Connection between two Facebook, I think. Check me if I'm wrong.
So friends would be our edges there. Whoever you have a friend with, there is some connection to in some capacity.
Yeah.
Yep.
Yeah,
About the Kevin Bacon game. Are we too young for the Kevin Bacon game? Who knows the Kevin Bacon game?
I do not know.
7 degrees.
Anyone want to either person who raised their hand? What's the Kevin Bacon game?
Oh, everyone in Hollywood has either worked with Kevin Bacon directly or someone that's worked with Kevin Bacon because he's been in like movies for 50+ years.
Yes. Yeah. So the question is, how far do you have to go between I worked with that person who worked with that person who worked with Kevin Bacon? So in this case, what are the vertices and what are the edges?
Like the first, the the celebrity.
Yeah, the person,
And then the links would be like the people that have been in.
yeah, that you've worked with, and that way you get some very large interconnected web of here's everyone in Hollywood in some very large collection, and the vertices are all of those people. The edges are if that person has worked with those people. So the question would be how many edges do you have to traverse before you can get to the Kevin Bacon node?
But wouldn't should those also be a possible question for the game? So wouldn't the like projects themselves be the edges?
Think of it that way. Think of it that way.
Possibly.
How about we have methods in a program and those methods call each other in some capacity or in some way, shape, or form. We kind of have an interconnected set of methods in a program. What are the vertices? What are the edges?
Well, the vertices would probably be the method edges themselves, and let's see, and I think the edges would be the trying to think of the words here. Oh yeah, the connect calls to each other.
Yeah, the method calls. So the methods themselves are the vertices. And within methods, you can see what method calls exist in this method. Those would be directed edges to another method. How about roadmaps?
Does anyone else want to answer? Not so sure myself, to be honest.
Usually.
Yeah.
Downtown Spokane might beg to differ. Yeah.
So, moving. I right type of roadmap. The like banning or something. It would be locations as the with edges as roads.
Okay, locations and roads. I'm even gonna go a step further and say either that or potentially intersections where roads would meet or cross. The idea would be that if we wanted to plan a route from location A to location B, then we would need vertices that represent what interconnected set of roads should we take in what order in order to get from intersection to intersection, so we could create that path. Routers.
Are usually for highway names.
Yeah, roadmaps would be, you have cities or kind of intersections of highways connected to other highways.
Yeah.
You should stay on this road until at least the next possible point where you could leave that. Yeah. Airline routes would be another example. Vertices are your cities or hubs. And the interconnected value there would be either, there could be many different possible edges here. It could be the amount of time to get from one to the other, the amount of money to get from one to the other, the distance from one to the other, any relative query on some amount of distance between these cities with respect to their connection via that airline. Family trees. So trees are a kind of graph.
I can kind of see it, honestly. The family trees, I think that, well. The branches to, that networks those other families would probably be the edges because it's connection and. Trying to think, what would be vertices though?
Yeah,
I would assume members would be vertices while lineage would be edges.
yep,
Yeah, that would work, thank you.
yep, you have people as your vertex and then connections. Children or parents usually is all we have in a family tree. There are more connections that exist, but they're not direct connections. If you want to say a grandfather, that's a parent's parent. The connection's usually directly to parents, directly to children. How about course prerequisites? The courses in a degree, how could that be visualized as a graph?
Well,
Could the courses be the vertices?
Courses or vertices, yeah.
yeah,
All the actual, prerequisite or the requirement be the edges?
Yeah,
yeah.
yeah.
Like,
In order to be enrolled in this class, you have to take some set of other classes. We could basically start the degree at one level of what are all the classes you can take with no prerequisites, and then from there build a graph of interconnected courses. So massive branch, so many, I haven't talked about networks or network connections. There are so much data that can be represented as a graph once you start thinking in terms of vertices and edges. So it's useful to know combinatorics and discrete math in order to get going with this, which is why they're prerequisites. So let's talk undirected graphs as a large study. So to be an undirected graph, our edges don't have directions. Edges are always two-way. If we can go down an edge between vertex A and vertex B, we can always get back to vertex A on that same edge. So we have a tuple that says there is an edge between vertex U and vertex B. That being a member of the set of edges tells us there is also a connection between B and U in our list of edges. It must be. One thing to note is that when we describe undirected graphs, we do not store both of the edges or both of the directions of an undirected graph. We just look for, is there a connection between these two? And there's implicitly a connection in the opposite direction. So you do not necessarily need to store both as long as we know that the graph is undirected. Next term you might care about is the degree of a vertex. This tells you how many connected vertices are there via some edge. So here is a colorful, very small graph. What is the degree of vertex A? 2. There are 2 nodes that are connected to A, B, and C. And again, these edges do not have any arrows on them representing directionality. They're just lines. They connect the 2. Degree of D is 1, degree of C is 3, degree of B is also 2. They're a little bit more straightforward. Any questions so far? All right, the other one we have are directed graphs. So in this case, edges do have a direction. Just because there's a connection between A and B does not mean there's a connection between B and A, or as I state here, between U and B. If the edge UV is in our list of edges, it is not implied that VU is in our list of edges. So now we can state further that U is the source and V is the destination of that edge. So in a directed graph or a digraph, edges have directions, they have sources and destinations. Once we have that, we can redefine the concept of degree to be an in degree or an out degree. The in degree is the number of inbound edges to that vertex, and the out degree is the number of outbound edges from that vertex. Let's again look at an example. What is the in degree of vertex A? 1
One.
out degree of A.
One.
Also 1 for vertex B. What's the in degree? 2 out degree.
One.
1. Fairly straightforward. Any questions on that? Yeah.
Is there a concept of a combined degree?
Not really. You could make that out of the in degree plus out degree, but we don't assign it a name necessarily. Because usually your query is how many inbound edges are there, how many outbound edges are there. All right. If we have a self edge, that means that the inbound and outbound part of that edge is to the same node. The edge loops from a vertex to that same vertex. There are many graph types that don't allow for that or limit the number of them, but there are also those that do not. Again, depends on what the graph is being used for. It would make sense that in some cases, self edges should not exist. Any example of a graph environment that you can think of where self edges make no sense?
Facebook friends.
That's the one I was going to go with if no one said anything. As much as I would like to be friends with myself, as soon as I allow that, it's a very slippery slope to, I'm very popular. All of my, 98% of my friends would agree that 98% of those friends are just me.
Folks in the library?
What are the edges in that case?
I was spitting from.
We could do research articles, in which case, if there's a reference from one article to another article, that would be an edge. Who's ever read a research paper that cited themselves? The same paper, not the same author or prior paper, but the same paper. You want evidence of what I'm suggesting or what I'm showing to be true in this paper? The evidence is in this paper.
So as stated above.
Yeah. Yeah. But if you go into the references section, you're like, I'm going to cite my own, this exact paper. This came from prior research. This paper.
Well, now I have no choice but to believe them.
I have a bootstrap.
Yeah. A connected graph is one where we can get from every vertex to every other vertex via some number of edges. Does not matter how many edges. But the idea is that if you were to now say we have a source vertex and a destination vertex, there would always be some path to get there. Since vertices and edges are sets, we use cardinality to define their size and the same notation that you would expect from discrete. So the cardinality of B is just the number of vertices in our graph. Cardinality of E, number of edges in the graph, just the size of that set. Intuition check. What's the minimum number of vertices in a graph?
One? No.
I like 0. You could have a graph with 0 vertices.
I almost said that, but I felt like that
One makes sense. And what is a 0 graph vertex?
yeah,
An empty library.
Facebook during conception. There were no profiles, except maybe some test profiles. But it could represent an idea, something that is scalable. The initial set, the initial point is 0. How about edges? What's the minimum number of edges in a graph? Let's now say there's at least one vertex. What's the minimum number of edges in a graph? It could still be 0. We could have a single vertex with no further edges connected to each other. So the minimum is not a particularly interesting question. But now we have something that's a little bit more interesting. The maximum number of vertices. That one is less interesting. Maximum number of edges is much more interesting. But maximum number of vertices, arbitrary, yeah. There's no real hard cap. But what about the maximum number of edges with respect to the number of vertices? Have the vertices minus 1 for each vertex. So we now have to figure out, is this directed or undirected? Let's start with the undirected graph. So every edge from U to V is also from V to U, so that's not two different edges. But let's figure this out.
And then with loops, then it'll be a number of vertices.
Each one could potentially link to the number of vertices. But again, if we have something between U and V, then we'd have to not see between V and U.
Vertices to the number of vertices.
Good guess. So let's start with, we're going to at least first disallow self edges, just to make the problem a little bit easier. We have one vertex. There it is. How many edges can we make? 0. We have 2 vertices. There they are. How many edges? 1. We have 3 vertices. There they are. How many can we get? 3. We have 4. There they are. How many can we get?
Well,
6. 1, 2, 3, 4, 5, and 6. So, anyone recognize this pattern yet?
Very familiar. The exponential?
That 3 to the power of n.
This is 1. This is 1 plus 2. This is 1 plus 2 plus 3. Wow, it's back again. Yeah.
Just n minus 1 times n over 2.
Yes, it's n squared plus n over 2. The same thing, the same triangulation formula that we've seen over and over and over again in this class. It just keeps coming back. But yeah, if edges are undirected, then that pattern will continue for an arbitrary number of edges. N squared plus n over 2, it's in order number of vertices squared. So whenever you see something in a graph, in an undirected graph, that says it's based on the number of edges, the worst case for the number of edges is the number of vertices squared. It's in that order. When you see something that is something like the complexity is based on B times E, something like this is not necessarily quadratic. This is in the order of the vertices cubed, because the edges could be up to the square of the vertices. Yeah.
You have self edges in undirected graph.
You can. It just kind of shows that to do this, I want to think about U of L, something like there is a class and there is some reference of this class to this class. That's where I've seen that before. So that would be possible. In this case, we're just adding V, the number of vertices, to these numbers. So whatever we get is just plus V, all the possible self edges. But now let's say that edges can be directed. How does this change?
It doubles.
Doubles. Everywhere there is a single edge, we can make that a direction and then have another edge that is back the other direction. So it would double. But whenever we double something asymptotically, it's the same order. So the number of edges are always in the order of the square of the vertices in the worst case. Now, this is not always going to be true, and we'll see that sometimes we can have certain assumptions about graphs that say whether we'll talk about sparse versus dense graphs. The concept of sparse is it's closer to the number of vertices is the number of edges. In a dense graph, we have closer to the number of the square of the vertices is the number of edges on the graph. That's how we define sparse versus dense, so that we can say that the edges are closer to linear or quadratic compared with vertices. But that again is problem dependent. Questions before we move on? two vertices directionally connected to each other. In a directed graph, they would be two edges if we had A connected to B and B connected to A, because in a directed graph, it's not guaranteed that we have a bidirectional edge like that. So it would count as two edges. It could just be that we have a link from A to B and nothing from B back to A. There's no edge back. So we need some way to distinguish from that. So be two edges versus one. Good question.
You only have one loop though, right?
Yeah. Yeah, you can't have two different edges, self edges, like from you to you and also from you to you. It's the same edge. We can define the concept of a neighbor. If there exists an edge, a directed edge, B is a neighbor of U if there is an edge from U to B. So directionality of the edge matters. You're only a neighbor if you can get there from the current node. So in this case, B is a neighbor of U, but U might not be a neighbor of B, depending on the directionality, how many edges we have.
That feels funny in like the city analogy, because like if you have a house and there's like a highway that goes all the way to someone else's house. Like,
Yeah.
are they neighbors?
Yeah, think of it like one-way streets. Like if you were down a particular one-way street and one block down, it's not a one-way street going the other direction. Imagine just a sequence of one-ways that all flow the same way. It's a lot harder to get once you go visit your friend because you have to find some path around back to your house, not the straight path you took to go get. All right, we can have weighted graphs. It makes sense that edges can define how close the vertices are to each other. So edge weights are the cost or distance, or it's some measure of how far apart these edges are. On a network, this could be ping times between servers. This could be relating to money or distance or throughput or really any query you could have between two vertices, whatever the vertices represent. Some graphs allow negative weights on their edges. What would it mean for there to be a negative edge weight in a graph? What does that intuitively mean? Potentially, you could basically say that if there's a cost to get in some kind of undirected graph, if there's a cost to get from U to B, you can undo that cost by going from B to U. So you could turn an undirected graph into a directed graph, allowing for negative edge weights. Work. Other ideas? Yeah.
Could you say it is better to take that edge than it is to do nothing at any time?
Yeah, we're defining something like cost of the activities that you go do when you go to a concert. That concert has a cost. On the other hand, you go to work, the cost of going to work is negative. You get money out of that. So it's kind of just the opposite of whatever it is that the edge is relating. So a lot of graphs don't allow for negative weights because it messes up particular kinds of algorithms that make an assumption that there can't be negative edge weights. So we'll see in a shortest path algorithm relatively soon that we cannot have negative edge weights because the assumptions that we make in that algorithm would mean that we don't necessarily find the best path if we don't make that assumption, which means that it cannot run on graphs that have negative edges. But we'll give you an example. Let's look at ferries on the west side. What do these edges represent? Travel times between ferries
Travel distances maybe too, but.
Yeah, it's the number of minutes of a ferry ride.
Oh, okay, let's. Oh, so that's what they mean by negative edge.
Well, not necessarily here. You would imagine that in that case, we take negative time in order to take the ferry between, so that wouldn't make sense in this graph.
Yeah, I get that,
Yeah, so some graphs wouldn't allow negative weights. If you were trying to model ferry travel times, it wouldn't make sense to allow for negative edge weights because what would that even mean?
Interesting.
We've invented time travel. In which case, what are we doing with ourselves? We should have many, many, many more important things to do than worry about ferry schedules if we've invented time travel.
That's true. First thing on the agenda, mess up the timeline.
Exactly. You were thinking about this. You go back in time to the point where these ferries were never invented. And then what are we even doing with ourselves?
Yeah.
Walking across the water. Exactly.
Dangerous thing.
So, all right, concepts of paths and cycles. So a path exists from some vertex to some other vertex. We'll call this v sub 0 and v sub n. If there is a list of vertices that we can traverse, so there's an edge connecting v sub 0 to v sub 1. There's an edge connecting v sub 1 to v sub 2, all the way to v sub n minus 1 to v sub n, such that we can get from v sub 0 to v sub n by traversing that set of edges. So that is a path. I can drive from this building to, I don't know, Spokane Valley Mall via some connection of roads. Each of those road connections would be an edge connecting those vertices, those intersections, such that if you do that in order, you have found a path from your source to your destination. Even though there's no direct connection, there is a path via a set of those connections. I shouldn't say set, it's a list of those connections because order matters here. A cycle, path that starts and ends at the same location, the same vertex. So let's take a look at a graph here. Let's first find 3 paths.
Multiple order.
Doesn't matter. Yeah, Seattle to San Francisco to Dallas is a path from Seattle to Dallas. Is it the only path? No, but it is a path that represents a list of instructions. Take the edge from Seattle to San Francisco. Take the edge from San Francisco to Dallas. This is one way to get from Seattle to Dallas.
You have a path from just Seattle to San Francisco.
You could. It is directly connected. There is a path. They are neighbors, but a path could involve more than just neighbors. It could involve more than that. Clarification. How about paths that are cycles?
Let's see.
Yeah,
Yep.
this is like a vacation. If you end your vacation in a different city than you started, you moved.
Yeah, and then-
Something went wrong.
Yeah, it's the same thing for like, say, Seattle, Salt Lake City, Chicago, then back to Seattle.
Yeah,
And you get where I'm going.
but they could be long cycles as well.
That's it.
Seattle to San Francisco to Salt Lake to Dallas to Chicago,
That's
Salt
it.
Lake to San Francisco to Seattle. That's a cycle with a cycle built into it,
Wow.
a subcycle. So path length here is just the number of edges. If the edges have weights, on the other hand, then those are path costs. So the sum of the weights of each edge gives us the path cost. Length, the number of edges that we traverse. The cost, the total sum of the edge weights of that path.
So when they decide to give me my, the price for like a ticket to like, let's say I was going Seattle to Dallas, that you would assume that the airline would just find the most expensive path.
Oh yeah, absolutely.
Okay.
It's not quite the most expensive path. It's the most expensive path that you are willing to pay based on all of your data. We could give you the $200 ticket, the $300 ticket. We know your budget. You'll pay up to $368.74, which is what we're going to charge after tax. What real data analysis is being used for. So here's an example of a cycle. We can find the length of that cycle. We'll say it's from Seattle to Seattle via San Francisco, Dallas, Chicago, and Salt Lake. The cost is going to be the sum of the edge weights. So 2 plus 3 plus 2.5 plus 2 plus 2. 5 total edges. These are probably hours of flights.
Yeah.
So if you could teleport from one plane to the next and it could immediately take off, then that is the cost of this exact flight path. Or the total amount of time in the air after you deal with all of the annoying layovers and boarding and deboarding processes.
I should see that example.
Questions on anything so far?
I don't have any questions related to this problem, but.
All right. Further terminology. Simple paths repeat no vertices. The first can be the last. So a simple path can be a cycle where you get from one vertex to another vertex at the very beginning and end. But a simple path does say that we can't have a cycle in the middle of it. We can't go back to, once we visit a vertex, we can't go back there. Then we said a cycle is a path that ends where it begins. So a simple cycle is a cycle that's also a simple path. That means that there are no sub-cycles to our cycle. Here we can say that a complete graph says that every vertex is connected to every other vertex. There's an edge. For any given pair that you could give me, there is an edge between those two nodes, those two vertices. So here is an undirected version of a complete graph. If it's a directed graph, then there needs to be an edge in every direction between those two nodes in order for it to be complete. Every possible place that there could be an edge, there is an edge. Another way to think of that. On the other hand, you can use strongly connected in a directed graph to say there's a path from every vertex to every other vertex. This just means there is a path. So here is a strongly connected graph. Any source destination pair, there is a route there. It's connected. Connected is defined in terms of just a generic graph, not necessarily a digraph. That says that we can get from every vertex to every other vertex. Strongly connected implies directed graph. And it's kind of that definition for a directed graph. Then weakly connected, there's a path from every vertex to every vertex, ignoring direction. So here is a weakly connected digraph. We can't necessarily get from every vertex to every other vertex, but if this were an undirected graph, then we could. All right, I hinted before that trees are also graphs. Trees are graphs with some extra constraints. But let's look at what those constraints are. We've studied trees, but a tree forces a graph to be undirected. There are some versions of tree that are directed, but in general, a tree does not necessarily have a direction. It's acyclic. In a tree, there is no way to get from a node back to that node or from a vertex back to that vertex. Imagine a binary search tree. Can we traverse from the root back to the root via its children? That makes no sense. There should be a single path from a root to a leaf.
Is
Yeah.
there anything like a doubly tree? Like how you have to double link lists, like you have trees.
Yeah, so if you have a search tree, an ABL tree like we did, that's a node stores its children and its parent, then you can get from a node back to itself by querying your parent's child. And that's a cycle that gets back to you. So in this case, it is more of a graph than a tree because you don't, as long as you have that parent connection.
Not putting incest. But I'm just thinking of like in terms of a family tree, you have two parents, so you could get from the root back to the root.
Yeah, no, it is a strange, what's the example? You can be your own grandfather. There's a way to do it. I don't remember it off the top of my head, but
So does that not count as a tree? It's not a perfect thing?
that would be kind of a weird definition of, yeah, ruining your own family tree. I'm the person who turned my family tree into a family graph. So tree must also be connected. You can't just have a tree node that is outside. You can't get there via the root. That doesn't make sense. Sorry?
That's what the orchids are.
Yeah. So yes, there's a kind of a single direction here. Trees are graphs, not all graphs are trees. So here's an example of a tree. How do we know this is a tree? It's undirected, it's acyclic, there's no way to get, there's no connection via following separate separate edges to get from a vertex back to itself. And it's connected, there's no vertex here that has no edges. You can get from every vertex to every other vertex. So this is a graph that is a tree. The trees that you've seen before, however, are rooted trees because one of these vertices is defined to be the root. So the trees we have studied in our classes have all been rooted trees, which means that we define one of the vertices on the prior slide to be the root. Then we can turn the edges into directed edges as flowing away from the root. And if you just have a tree as a graph type object, you define a tree. If we choose the root, it turns this into a unique rooted tree. So in the prior example, we decide that A is the root. It turns the tree that we saw into the rooted tree that we see here on the right. Whereas if we pick a different node for this, let's say we pick F. Then the tree becomes another unique rooted tree where F is the root, and we just flow everything away from F. G and H and C are all of its neighbors, so they become its children. And from there, we look at the number of steps away from the root, and then at the number of levels away from the root that we have in the rooted tree. Questions on this? Yeah.
The arrows are just stylistic, they're not arrows now direct.
It is meant to be a directed graph. As soon as you have a rooted tree, then that direction makes sense. Everything flows away from the root. By definition, there are no edges into the root. Representing the root is a child of some other node. If you're storing a parent, which is kind of the reverse edge, that's an exception that we allow for if we're storing parents. But in general, that root does not have any incoming edge. So we just kind of turn the undirected edges into directed edges flowing away from the root. Right, I think we're basically out of time.
Oh, yeah, pretty much.
So we'll come back to this tomorrow. 5 office hours starting now. If you have any questions on the material we've gone over today, the material that you have assigned, anything else?
Actually, there's no questions I quickly ask before we all leave.
Yeah.
So for the assignment after, where are we gonna start that next week or?
Yeah, it should be pretty sequential. I want it to be for the exam.
Yeah, so. Fine to ask those feature and. Write myself a video, or done during the week, but. Not. I haven't got the turn, there, but now turn to the, we get the truth thing, file upload, you know, with. Everything takes it regarding. This week's to we do assignment, but I know it works, so. And then I did a little bit more uniquely than Planks.